Okay, page 79. So if you're still on your phone, you'll want to be off your phone. And you'll want to be on page 79, 79. And today we are looking at gases. This is going to be the other part of what is on your quiz on Friday. If you remember, on Friday, there's going to be a quiz including finding molar mass of the unknown, finding the density or using those using density as a conversion factor, molarity, finding molarity, using it as a conversion factor, and then this last part, gases. So, Gay-Lussac, Monsieur Gay-Lussac, he was one of those extraordinary figures in the history of science who could truly be called an adventurer. He was interested in lighter-than-air balloons, and in 1804, he made an ascent to 23,000 feet. Think about that. That was more than 2 centuries ago. Up 23,000 feet in the air. An exploit that set the altitude record for several decades. To better control his lighter-than-air balloons, Gay-Lussac, yes? Oh, we got a phone call. Hello. Yes. My phone is like in the opposite side of the room, so yeah. No worries. No, it's real nice. That's okay. It's gonna be my class track first period. Yeah. Bye. Okay, so we were talking about Monsieur Gay-Lussac, and he is building these lighter-than-air balloons, and to better control them, he carried out several experiments on the properties of gases. And in 1808, he discovered the law of combining volumes. So what he discovered is that at any given temperature and pressure, so as long as those are the same, if you have gases reacting with one another, so if you have gases that react with one another, they're going to be present in small whole number ratios. So you're not ever going to have like 1 liter of hydrogen reacting with 13.783 liters of oxygen. It's always going to be like 1 liter of hydrogen and 2 liters of oxygen, or 3 liters of nitrogen and 4 liters of oxygen. Nice small whole numbers, okay? And they'll react perfectly with each other and there won't be anything left over, okay? So for example, when he kept the temperature and pressure constant, 1 volume of hydrogen gas, and you can see that here, we've got that 1 hydrogen, is that represented by that cube, plus 1 volume of chlorine gas. When it reacted, it produced 2 volumes of hydrogen chloride. So if he had had 1 liter of hydrogen and 1 liter of chlorine, he got 2 liters of hydrogen chloride. If he had 10 liters and 10 liters, he got 20 liters. But the ratio is those nice small whole numbers. So later on, Amedeo Avogadro, and yes, that is Avogadro of Avogadro's number fame, he came up with a hypothesis. Okay, so Avogadro's hypothesis, and this is very important. Equal volumes of gases, as long as that they are at the same temperature and the same pressure, contain equal numbers of molecules. Okay? So how can we represent that so you can like kind of visualize it? Well, what we're going to do is we're going to start with the smallest numbers possible. We're going to say, let's assume we have one molecule of hydrogen, yeah? And it takes up a certain volume. Well, then, how much volume does chlorine take up? Even though it's a bigger molecule, it still takes up the same amount of space. And that's because gases are actually mostly empty space. These look enormous, don't they? Right? But how big are actual gas molecules? They're like so small. So you can imagine if that was like the hydrogen and that was like the chlorine, and I don't even know if you can see those little teeny tiny dots that I've drawn on there, that's more representative of how much space the actual particle would take up compared with the empty space. Okay? But one volume of hydrogen contains one molecule. One volume of chlorine contains one molecule. And when you have H2 plus Cl2, do you guys remember what kind of a reaction that is? Think about that. Chat with your neighbor for a moment. What kind of reaction do we have when we take an element and we react it with another element? There's single replacement, double replacement, synthesis, decomposition, combustion, and neutralization. Good thing we'll be learning this in the next unit because we've forgotten since grade 10. Been a little while? Yeah. Okay, when you have an element and an element, have you guys heard of the instrument, a synthesizer? Yes? Okay, synthesizers take all sorts of different sounds and put them together. Yeah? A synthesis reaction is where you take two elements and you put it together. You might have heard of synthesis when they're talking about like an English essay. How well did you do in synthesizing the ideas, in bringing the ideas together? Okay, so synthesis means bringing things together. So when you combine two elements together, that is a synthesis reaction. So an element plus an element is synthesis. You might as well start learning this now. Start reviewing it because, like I said, after the mole, we are doing reactions. Now, when you take an element and you combine them together, what do you get? You get a compound. Compound. Yeah? And we know that hydrogen is H2 because H2 is one of the diatomic elements, Dr. Brinkelhoff, and chlorine, Dr. Brinkelhoff. Okay, those are both diatomics. That's why we have H2 and Cl2. Then when they form the compound, hydrogen is going to form an ion. It's +1. Chloride is going to form an ion. It's -1. So the formula for that compound would be HCl. Okay, but because we have 2 hydrogens and 2 chlorine, do you remember how to balance that reaction? 2. We put a coefficient of 2 at the front there. So we have 1 hydrogen molecule, 1 chlorine molecule gives us 2 hydrogen chloride molecules. Okay? And because each molecule takes up the same amount of space, 1 volume of hydrogen plus 1 volume of chlorine gives 2 volumes of HCl because you've got 2 molecules of HCl. Okay? So the ratio between the particles is the same as the ratio between the volumes. All right, here's another example, just so we don't have, everything be all the same. We can have 2 volumes of hydrogen gas. Okay, so that is H2. We have 1 volume of oxygen. So 2 volumes of hydrogen is the same as here 2 molecules of hydrogen. 1 volume of oxygen is 1 molecule of oxygen. What kind of reaction is this? Talk with your neighbor. What type of reaction is this? You guys kill me. What kind of a thing is hydrogen? It's an element. If it's an element and an element, just like the previous example, it is synthesis. And we get the compound that is made out of those 2 elements. And if we've got hydrogen and oxygen, the most common compound to get is water. You could end up with hydrogen peroxide, but it is not very likely. H2O. Now, if we want to balance this, we can take a look at it and we can say, I have 2 hydrogen on the left and 2 hydrogen on the right. But I have 2 oxygen on the left and only 1 oxygen on the right. How do we balance that? Tell your partner, how do we balance that? How do I make the oxygens equal on each side? We're going to add a coefficient. Okay, we're going to add a coefficient of 2, which means that now we have 2 times 1 is 2 oxygens, which matches the 2 oxygens over here. But what have we done with our number of hydrogens? We now have 2 times 2 is 4 hydrogens. So what do we need to do over on the right-hand side? Or sorry, the left-hand side. What do we need to do over here? We again need to put a coefficient, a 2 there, so that now we have 2 times 2 is 4 hydrogen. Now we have 4 hydrogen on each side. We have 2 oxygen on each side. Everything is balanced. You cannot have atoms appearing and disappearing. It just doesn't work. Does that make sense? Okay. But like I said, this is the next unit, but it's worthwhile having a little preview because that way your brain will start waking up to those ideas again. You cannot change the subscripts. Water, you can't be like, oh, I need 2 oxygens, so I'm going to change water into H2O2. Because now you don't have water, now you have hydrogen peroxide, and that is a completely different thing. Okay, so never, ever, ever change your subscripts. You can only change coefficients. And don't worry, if it's not making sense right now, whole unit on it coming up. It'll all become clear if you've forgotten stuff. So 2 molecules of hydrogen, 1 molecule of O2 gives us 2 molecules of H2O. And that means because volume and molecules are proportional, 2 volumes of H2, 1 volume of O2 gives 2 volumes of water. Those ratios are the same whether we're talking molecules or whether we're talking volumes. Do you know what else is the same? What if I gave you 2 moles of H2? How many moles of O2 would you need? You would need 1 mole of O2. This is just another version of the mole ratio.
Oh, yes, this is what we did in our science project.
Yeah.
We didn't use molecules, we said moles.
Yes.
Yeah.
Yes. And then we have 2 moles of H2O. The reason to use molecules is it's easier to visualize them, right? But obviously no one's ever going to have just like 1 molecule of H2 hanging out by itself. Like that's just, the world is not like that. There's just way too many of everything, all the atoms and stuff. Okay, so the ratio is 2 to 1 to 2. volume, 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 molecule, 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 mole, mole, mole. The ratio is the same, no matter which of those you're looking at. If you're having trouble visualizing why this is still the same ratio with moles, if we scale up, here we have 1, 2, 3, 4, 5, 6 H2s. Yeah. Here we have 1, 2, 3 O2s. And we have 1, 2, 3, 4, 5, 6 H2Os. Yeah? Well, that ratio is going to simplify to 2 to 1 to 2. Yeah? And if instead of writing the word mole, if I said, let's say I had 6.02 times 10 to the 23 O2s. That's 1 mole, right? 1 mole. How many molecules of H2 would we have? And you don't have to give me the actual number, you just have to say, what would you do with this number to figure out how many H2s we have? You would need to do the particle ratio, right? And how many hydrogens are there for every oxygen? There's 2 hydrogens for every 1 oxygen. So if we take 6.02 and we multiply by 2, we get 12.04 times 10 to the 23 H2 molecules, right? And that is 2 moles. And that's 1 mole. Yeah, we'll put it, I'm not going to put it into scientific notation because it's more visual that 12 is twice 6. Do you know what I mean? It just looks better that way. Normally, yes, I get really wound up about it being in scientific notation, but this just makes it easier to visualize one being twice the other. And if we're making 2 volumes of H2O, we're going to make twice as many particles as we have of the oxygen. So what is the number of H2Os if we have 6.02 times 10 to the 23 oxygens? What is this number here for the H2O if we have this number of oxygen molecules? And remember, we have a 1 to 2 ratio. 12.04. Again, there's twice as many, right? We had 6 waters for every 3 oxygen for every 6 hydrogen. So we can say we have for every 6.02 times 10 to the 23, there are 12.04 times 10 to the 23 H2O molecules. And that there is 2 moles. So this is the big idea of the whole thing, is that if you are at the same temperature and pressure, 3 oxygen molecules is going to take up the same space as 3 hydrogen molecules. It's going to take up the same space as 3 water molecules. 1 mole is going to take up the same of hydrogen, will take up the space as 1 mole of any other gas. So let's say that now we're going to pretend that this is 1 mole in here, okay? Okay, that's 6.02 times 10 to the 23 helium atoms. I want to draw your attention to the word atom versus molecule because I had a few people on quizzes doing things like saying atoms of C12H22O11. That's impossible. possible because an atom is a single boop. Yes? A molecule is a multiple. Yeah? So you cannot have atoms of a big particle because a big particle is made of many atoms. Okay, just watch out for that. All right, so over here we have balloons. They're all the same size. This contains 1 mole of helium. And what is the molar mass of helium? 4.0 grams per mole. So this balloon, if you take away the mass of the balloon itself, weighs 4 grams. Yeah? This balloon, it contains 1 mole of NH3, which is 6.02 times 10 to the 23 NH3. Are those molecules or are those atoms? NH3. Take a look at them. Are those molecules or are they atoms? Those are molecules. And what is the molar mass of NH3? Everyone, calculate it out. It is 17, which means that this down here is a typo. Cross that out. I need to fix this. That should say 17 grams, okay? Not 15 grams, because nitrogen weighs 14 and each of the hydrogens weighs 1. And finally, we have this guy over here. This is oxygen. This is 1 mole of O2. Oxygen is one of our diatomics, which is 6.02 times 10 to the 23 O2 molecules. And the molar mass of O2 is, what's the molar mass of O2? 32. What's the unit of molar mass? Grams per mole. So I don't know if you guys caught it, but I made a mistake up here when I said that the molar mass of NH3 was 17.0 grams. It's 17.0 grams per mole. That was my boo-boo. I'm sorry about that. Okay. And you can see here we have oxygen, and this little balloon without the mass of the balloon is 32 grams. Is that ratio of masses 1 to 1 to 1? Because we have 1 volume, we have 1 volume, we have 1 volume. Yeah? We have 1 mole, 1 mole, 1 mole. Those ratios are the same, right? 1 to 1 to 1, 1 to 1 to 1. Is 4 to 17 to 32 the same ratio? Is that a 1 to 1 to 1 ratio? No, obviously it is not. So the key idea here is that although you can use that same ratio, 1 to 1 to 1, for both volume and for moles, you cannot do it for grams because everything weighs a different amount depending on how big the atom is, you know, how many protons and neutrons. So the mass ratio is not the same. So that's just been a lot of thinking about gases, okay? And we can see here, we have another example where we're just showing that the pressures are all the same.
So pressure is like what, one atom per molecule?
Pressure is the force over the area,
Oh.
okay? So pressure is the force over the area. And basically what pressure is, it's how hard the molecules are bashing into the sides of the container,
Oh.
okay?
So they essentially, in order for like for there to be like, what would they call it? In order for Avogadro's hypothesis
Yes,
true,
yes,
all of the atoms must bash against each other at the equal pressure.
yes, they all need to be bashing into the sides of the container with equal force. Yes? Yeah. And that's going to depend on their speed and their mass and all kinds of more complicated things. But as long as you're okay with the idea that as long as they're at the same pressure, they will and temperature, they will have the same number of molecules in each of them.
What if there's like 2 ATMs?
If there's 2 ATMs, then it's going to have either twice the temperature or twice the number of particles.
So okay, so the ATM, the particles.
The atmospheres is the unit of pressure.
Atmospheric temperature and the molecule
Yeah.
have to have a 1-to-1 ratio.
Yes. Okay, so as long as pressure and temperature are the same, so as long as these are the same, then the number of molecules are also the same. Oh, and actually the volume has to be the same. Okay, so if you've got the same volume, the same temperature, the same pressure, then the number of molecules are the same. And this is only for gases. And that's because gases have so much empty space in them that they end up taking up the same amount of space no matter how big the molecules are. Okay, that's an oversimplification, but you don't have to worry about that until you're in university. So we're just going to simplify, okay? So now most often in chemistry, to make our lives simple, we are going to pick one temperature and one pressure to measure all our gases at least for chemistry 11, okay? And that particular temperature and pressure are called the standard temperature and pressure, which abbreviates as STP, standard temperature and pressure. And that is 1 atmosphere. ATM stands for atmosphere. That's a unit of pressure. And 0 degrees Celsius. Okay? And if you were doing anything else with this, you might know that that's 273 degrees, or sorry, not degrees Kelvin, just Kelvin. We're not going to worry about Kelvin in grade 11 chem. Okay? But if you're interested, it's 273 Kelvin. So standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. Do you think you need to memorize that?
Yeah.
Yes. But they're really easy. It's just 0 and 1. Yes? Yeah. 0, 1. So here we go. At STP, at this standard temperature and pressure of, what's the temperature?
No, it's 0 degrees.
0 degrees Celsius. So at 0 degrees Celsius, and what's the pressure? 1 atmosphere, which just so happens to be the pressure at sea level. Okay, so if you're at sea level, the atmospheric pressure is 1 atmosphere. So if you're up on the top of a high mountain, do you know what happens to pressure when you get up on top of a high mountain? It becomes less because air pressure, the atmospheric pressure, is how much gas is pressing down on you. So if you took the entire atmosphere going up to the end of the atmosphere, all that gas is pressing down on you right now. And because we are close to sea level, it's pressing down on you with a pressure of 1 atmosphere. But if you go up a mountain, it's pressing down on you with less, okay? Because there's less of a column of air above you. It's just, you're closer to the top of it. With a barometer. Barometers measure pressure. Yeah. It's quite an interesting thing. If you're ever interested, I'll show you. Not right now, but yeah, I can show you how they work. Kind of cool. At any rate, as long as we're at 0 degrees Celsius and 1 atmosphere, then the volume is equal to, and if we have N is equal to 1 mole, remember N is the number of moles. If N is equal to 1 mole, then volume is equal to 22.4 liters. And guess what that gives us? That gives us a conversion factor. Because 22.4 liters of a gas at STP is how much space is occupied by 1 mole of gas at STP. Yes? And we can simplify that by just saying the molar volume of a gas at STP is 22.4 liters per mole. And we're back to the one going with the mole. So now, how many conversion factors do we have now? I think this makes 7. 7 conversion factors. Okay? And if anyone is interested, we have our 7 conversion factors. You should be able to tell me the first 4 really easily because we've done so much with them. What is one of them? Particle ratio. What's the one that's just like the particle ratio in terms of its number? The mole ratio. What is another one that we learned early on? Sorry? Yeah, we got molar mass, and we have, what was the other one? Avogadro's number, molar mass, Avogadro's number. We have molarity. And we have density. And now we have molar volume. Now, if you remember, molar mass is the mass per 1 mole. Molar volume is the volume per 1 mole. So this would be grams per mole, and this one is liters per mole. And molarity is moles per liter. Okay. I can print this out if anybody wants a copy later. Okay. So molarity is some number of moles per liter. Density is some number of grams per liter or some number of grams per milliliter or some number of grams per centimeter cubed. Avogadro's number is molecules per 1 mole. Mole ratio is moles of A, moles of B. Particle ratio is just A to B. This is not very tidy. Okay, but it does give you all your conversion factors. And I think in your book, let's see if it's in there.
You need that chart?
I think there's a chart.
We do have a chart.
Yeah. So on one of these pages, it's going to be near page, probably page 1 or 2 or 3. Oh, here it is. So it's on page 2 in your book. We have Avogadro's number, we have molar mass, we have molar volume, we have the particle ratio, the mole ratio, we have density. What have I missed here? Molarity. And that's it. 1, 2, 3, 4, 5, 6, 7. These are just another way of writing them. So there are 7, and that's going to be it. There's only 7 conversion factors, and you have now learned them all. Okay? Now, we got to do stuff with that last one. So, let's try this example. By the way, I think I have fixed the workbook. So it always says at STP. But if I haven't, you can assume that if it is a gas, that it is at STP, unless I tell you otherwise. So if I've missed it, do let me know so I can fix it. But you can make an assumption that you're at STP. So what is the volume? What is the volume in liters? So it tells us we don't want milliliters, we want liters, of a 2 mole sample of methane at STP. Now, it does not say methane gas, but if we mention STP, you can assume it is a gas.
Like in the speech, like iodine gas, carbonic acid, and now we're going to have to see with the STP.
Yeah. Okay, so for this one, and if you're wondering where we are at the top of page 82. Top of page 82. Okay, so we have moles. We don't want moles. We want to cancel it out and find liters. And this is 2 moles of a gas. And when we have a gas, we will use 22.4 liters of a gas per 1 mole of gas. And I'm going to put those there just so that you remember that you can only use this with a gas. Can't use it with solutions, can't use it with solids, not with liquids, only gases. Okay? So there are moles, liters, 22.4 liters per 1 mole. And you remember how everything up till this point has been as easy as 1, 2, 3? Well, this is as easy as 2 plus 2 equals 4, 22.4. Okay, so it's not quite the same, but again, it's going to help you remember that it's not like 24.2 because 2 plus 4 does not equal 2. Okay, 2 plus 2 equals 4. And we do that and we get 44.8 liters. Did we like that? Was that difficult or was that easy? Oh, liters of what? Liters of methane, CH4. Yes? Okay, cool. Now, here's another example. Roll screen. How many moles of ethane? Oh, this is terribly worded. I have not fixed this at all. This should say how many moles of ethane gas. So let's fix this. At STP. Okay, that should all be in there. My apologies. I really need to fix that. How many moles of ethane gas at STP are there in 5.60 liters of ethane? So, how many moles is equal to 5.60 liters of C2H6 gas? What unit needs to go on the bottom? Liters. And on the top, we want moles. And because it's a gas, we know there are 22.4 liters per 1 mole. Remember, other than molarity, the 1 goes with the mole. 22.4. And we get 5.60 divided by 22.4. And I don't know what that is, but the answer is over here. It is 0.250 moles of C2H6. Okay? We're not going to practice these just yet because there's not really much to them. Hi. Okay. Well, actually, let's just go. Just before we do that, grab your purple sheet. Okay? Grab your purple sheet. And let's just take a look at what we learned today. So I'm erasing all the stuff that we did yesterday and the day before and whatever. Today we have learned how to go from the volume of gas at STP to the moles of A, and that's using 22.4 liters per mole. Now, where could you go from there? Where could you go from moles? You could find the grams. You could find the particles, not the molarity because that's a solution, right? And we're dealing with a gas. But you could then find particles B. Maybe you're like, oh, how many oxygen atoms are in the CO2 or whatever. Okay, so once you get to moles, all the tools that you already have are at your disposal. Okay, so we've just added on one extra way to get to the mole. All right, so we now have 4 ways to get to the mole: from particles, from grams, from molarity, and from volume, and from volume. All right. 5.5b, page 85. Okay. Remind me, what is a unit for density? Remind your partner, what is a unit for density? What's on the top for density? Grams. Yeah? What goes on the bottom for density? Volume of some kind, okay? And in this case, we're going to say density is grams per liter because that's going to make our converting between that and molar mass really easy. What is the unit for molar mass? Grams over moles. Ooh, look at that. Grams for both of them are on the top. if we have a gas, can we convert liters to moles and moles to liters if we have a gas? Yeah, we sure can. Yeah. So if I give you the density, you're going to use 22.4 liters per mole to find the molar mass. If I'm giving you molar mass, you can use 22.4 liters per mole to find the density. Okay, let's take a look at this. Okay, so we're going to find the density in grams. Per liter at STP for methane, CH4. Okay, and you might look at this and you'd be like, oh my God, she's given me a question and there are no numbers. Oh dear. No numbers. What on earth do I start with? You're going to start with the periodic table because the only thing you can find out about this is its molar mass. So let's find the molar mass of CH4. We have 1 carbon, we have 4 hydrogens, so that's going to be 1 times 12 and 4 times 1. You don't have to write this all out, you know that. Okay, 4.0, and when we add those two together, we get 16.0 grams per mole. Please, please, please keep that 0.0 on there. There's still a few people who are forgetting it, and it will cost you a half a mark every time until you start remembering. Okay? Don't let it mess you up. Okay? So now, if we know the grams per mole, we want to find density, which is grams per liter. But we have 16.0 grams per mole. Well, if I want liters and I don't want moles, where do the moles have to go in my conversion? They have to go on the top, right, so that they will cancel out moles. And what's going to go on the bottom? Liters are going to go on the bottom, so we'll end up with grams per liter. And this is a gas at STP, so we know there are 22.4 moles per liter or liters per mole? Liters per 1 mole. The 1 goes with the mole, unless it is molarity. Okay, so 1 goes with the mole, 22.4 goes with the liter, and 16 divided by 22.4 is 0.7143, which would have to round to how many sig figs? 3 sig figs, so that's going to be 0.7143. And what units are we left with? Oh, that was foolish of me. I rounded to 3 sig figs by leaving 4 sig figs. That's crazy. Okay. Our units that we have left are the grams on the top and the liters on the bottom. So that's going to be grams per liter. And do you see how if you've got your units everywhere, they all just sort out lovely? Yeah? Okay.
So you use the molar mass.
Use molar mass to find density of a gas.
Density of gas, that's the conversion factor.
Yeah. Use molar mass to find density of a gas, and your conversion factor will be the molar volume, 22.4 liters per mole. Okay, let's do an example going the other way. Okay, we have a density of an unknown gas. Okay. The density of an unknown gas is determined in the laboratory to be 4.22 grams per liter. Remember, anytime you see this, you should be rewriting it as 4.22 grams over liters, yes? Okay. And we want to know the molar mass of this gas. So far, you can find a molar mass by using the periodic table, if you know the formula. Do we know the formula? No. We can find the molar mass if we have the mass and the moles. Do we have the mass and the moles? Not really. We have the molar mass, but we can get there, right? Because we want to know the molar mass. And molar mass is the grams per mole. And we are going to start with the density, which is 4.22 grams per liter. We want to keep the grams. We don't want to keep the liters, so where do liters have to go? They have to go on the top. And then we want to have moles on the bottom, so we need to put moles on the bottom. And remember, it's not molarity, so the one goes where? With the mole. Yeah. And then that's 22.4 liters because it is a gas at STP. Do the calculation and you get 4.22 times 22.4 equals 94.528. Tell your partner what that answer is to correct sig figs with units. It might not be an element, it might be a compound.
Oh.
Right? Okay, 3 sig figs, so 94.5, and the liters cancel out, and we're left with grams over moles. And that is the molar mass of that compound. And I don't know what that compound is, but we've now found its molar mass. And if I gave you a list of compounds to choose from, you would find the one with the matching molar mass and say, aha, it is that one. Yes? You could actually do like an analysis at a crime scene if there was like some gas that like toxified people and you're like, oh, I wonder what that gas was. And you could find its molar mass using this. And oh, it's so exciting. Just like CSI. You guys don't know CSI. You're too young, aren't you? Anyone know CSI? Oh, very good. Good TV. Good TV from the golden age of television. Oh, no, CSI, a crime scene investigation. So good. All right. So today you guys are going to be doing on pages 82 to 84.
And also, so like say you have oxygen or you have hydrogen, they will always be in diatomic form even in gas, right?
Yes. If they're in a compound, they won't be diatomic. They're just whatever the compound works out to be. Okay. So folks, 82 to 84, odd numbers only, but you'll notice it also says, oh, just 1 second. If you are a super converter, you can just do 11 and 12. Right? Because you're like, man, this is boring, right? And you can maybe just do 11 and 12 or work your way backwards, okay? Now, we're also going to get you guys to do, maybe not all of these today, but let's see. Let's get you to do page 85, 86, number 1 and 2. Or more, if you want to do more.
Are we essentially like done the unit?
We have dilutions. We have dilutions and we have empirical and molecular formulas, but I might not make that enriched. or we might come back to it like at the end of the year if we have time,
Right. But
right?
do you think we're going faster than your other year?
No,
Going slower?
no, we're about the same. Yeah. I try hard to go faster because I never get through as much as Mr. Wu and Mr. Wu, Ms. Wu and Mr. Weinberg, but I never manage it.
Oh.
I try to go faster and I do not manage it.
It's alright. I like the people stuff.
Yes.
Wait, Jacob, that Jacob is science teacher?
Huh?
That Jacob is science teacher too?
I have no idea.
Oh, Jacob.
Oh no, different Jacob.
Different.
Different Jacob. Not my class, but I know who he is because he comes in and sits in here during that block. It's not, I don't teach here in block 1.
I didn't get all the things that all I could lose. So I was running around so much. Yeah. I was afraid to and he's like, so you're gonna get with me. So, and they're not nice. And the first two groups, they're like, I just yelled from across class. I was sprinting on like mom. People didn't know how to feel about it. And sometimes you can but other times, I love them so much, and they're gonna told and when they're so nice, so they're like, oh, I just love these people, right? And they're just so beautiful. Yeah, like, and it was one of my friends who listened to it, and they're like, and what is all of these ones? To others, and respectful of yourself and your environment. And there's so much. Oh my goodness, so much, Mama. I'm like, just so we all hated fun. I don't want to hear my class. Girl, we would hit each other against the wall. That one group of all those boys from it, like, yeah, yes, all the drama. Yeah. Now, Andy, I mean, this quiz. Yes. Were you make a solution? Do that. Yeah. The quiz. I was there. On that lap, isn't it? Let me double check. Let me double check. There's one quiz that's missing. Okay. Andy, yeah, it was the quiz on making a solution. So that is, and I need to get you back your moles, grams, particles quiz if you don't already have that. So let me see if I can find that for you. Did you already get that one back?
No.
Like this one? Did you get that one back? Yeah? Okay. So yeah, would you like to write that making solution quiz today, or would you like to do it tomorrow flex, or what works for you?
Quick today. Common cancer.
We have about 10 minutes left.
I think it's not.
Not enough? Okay, that's fair. That's fair. Do you want to do it tomorrow?
Yeah, tomorrow.
Okay, perfect. Good. Thank you. Who else is missing quizzes?
My great grandma at some point she still walks through the concrete. Oh, I forgot about that.
Yeah.
Sure. Yeah, no problem. Yeah.
Hi.
We do a lot of quiz work.
Yeah.
You know what class is over?
Pardon me?
You know what class is over?
Class is over, they tell me the orgy. 41. So,
Probably do it. If you can't, you can, grab it at some point. Oxygen's diatomic.
So it's more twice as much.
Yeah, folks, watch out for your diatomics in the gases because they're going to come up and bite you quite often.
Sure.